Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. So in this video, we're going to be talking about pedestrian bridges and the principles of those bridges according to the standards that we are using, or personally I am using, as an introduction to the future videos that we are going to do in Robot when designing those pedestrian bridges. Now, bridges are one of those topics that are close to my heart. Partially my research is about bridges. However, my research is usually about highway bridges. So this is a pedestrian bridge, which should basically be a little bit different. Now, when it comes to bridges, there is usually one code that stands immediately out. Of course, I'm talking about American codes because my work and my education is in the American standards. And whenever you say bridges, the first thing that comes into mind is called the AASHTO code, which is the American Association for State Highways and Transportation Officials. This AASHTO code is like the go-to code when it comes to designing bridges. Now, I am referring to the LRFD version of this code. If you open the AASHTO code, the LRFD, you will see that the code talks about pedestrian bridges. However, it doesn't really tackle the pertinent questions when it comes to pedestrian bridges, like what is the load and what are those things that you should take into account. Now, that's true, it doesn't tackle them, but it gives you a reference. And this reference is called the LRFD Guide Specification for Design of Pedestrian Bridges. Now, this is a guide that is available for the design of pedestrian bridges, and this is also being referred to in all those specifications of all those transportation departments. For example, here, this is the Wisconsin Department of Transportation, and the Department of Transportation is one of the ruling bodies in the USA for giving manuals that engineers should stick to when designing bridges or anything related to transportation. And this 6-page document is an amazing document that tries to summarize everything under the sun here. So it talks about structure selection, it talks about all the types of structures you need to take account into, and it talks about the design specifications. And as you can see, the AASHTO LRFD and the AASHTO guide are basically those used. Now you can see that it tries to give you the most important points here that needs to be considered. For example, here, the pedestrian live load PL should be as follows from the guide, which is 19 PSF. This is Article 3.1, and there is no dynamic load allowance. Now this is a lot to be unpacked. I will unpack most of it, not everything, because it takes time. Some of those, while I'm doing robot, some of those things will get clearer and clearer when I start doing a highway bridge, because partially I am planning to make a highway bridge later. But for now, I want to do a pedestrian bridge because it's somewhat easier in my humble opinion. Once this is done, we would have grasped some of those ideas in the bridge domain, and then we can extend to the highway bridges and see all the nuances and problems that are related to that. Then you can see that there is a pedestrian live load as 19 PSF. We need to convert this into pascals. I will think about the conversion later. There is no dynamic allowance, and there is also a single maintenance vehicle. I'll talk about this in a moment. Of course, sometimes you don't need a maintenance vehicle. I'll come to that anyway. So you can see it's relying heavily on something called the design pedestrian bridges. Now, unfortunately, I do not have access to this guide, but what I have is its draft. It's draft of that design. This is readily available. This is available on the internet, and you can see that this is really, at least this is the free version that reflects the design guide quite well. For example, in 3.1, Article 3.1, you can see that it talks here about 90 PSF, which is exactly what those guys related when they went to the actual, not the draft, the actual pedestrian bridge design. For example, it talks about the maintenance car, which is this thing, which is H5 and H10, as you can see. Of course, I will talk about those later, especially when I model. And you can see that you have two widths, from 7 to 10 and over 10. And if you go here, you go down, you see that, well, from 7 to 10 and over 10. So I think this is a very good draft of the final code, and this is freely available for you. For me, I have a very good close approximation, a free alternative, which I will basically upload or give you a link in the description. All right, so there is a lot to unpack here, and remember, usually I start with a theoretical background before I start diving into robot. I think it could also be beneficial if I take all those theoretical introductions and make a video series out of them, just cut them off my videos from robot. Anyway, I speak to my editor to talk about this, and he should cut me some slack. I mean, the dude is roasting me. Let's hope that he sees it and basically replies to me when he's editing the videos. Anyway, he's a nice guy, but sometimes he messes up. Anyway, uh, all right. So there is a lot to unpack, right? There is something called live load. There is something called dynamic load allowance, exactly. And there's a lot to be talked about. So what is happening here? Well, first things first. The dynamic load allowance, as cool as the name sounds, is just a factor. So the dynamic load allowance is just a cool name for a factor that is used in the AASHTO highway bridges. And please notice the relationship between the pedestrian guide and the AASHTO LRFD code. The pedestrian guides the pedestrian guide only outlines some conditions that need to be taken into account in the LRFD code. What I'm trying to say is that the LRFD code is what will govern your design when you deal with bridges, if it's pedestrian or not. And the pedestrian design guide is what just gives some nice inputs and answers some pertinent questions when it comes to designing pedestrian bridges because they are a special case. So in the AASHTO LRFD, there is something called the dynamic load allowance. I will be talking about this later when I talk about highway bridges. Luckily for you, you should not take this into account. It means the load factor is 1. But what is the idea of the dynamic load factor? Well, as the name suggests, the dynamic load factor comes to talk about the dynamics of moving objects on a bridge. Meaning, let's say you have a bridge that just spans from this point to this point. Just a little bridge like this. Just have a bridge that spans from point 1 to point 2. Of course, I'm very simplifying here. Now, when a car moves, it usually moves in the direction of the bridge. I don't know, like 50 kilometers per hour, 100 kilometers per hour. When it moves on a bridge, the bridge surface is sometimes uneven. It would have some bumps up, bumps down. It's not perfect because there are imperfections in our work. Now, what happens when a car moves on this surface? Sometimes it goes a little bit down with the surface, and sometimes it goes a little bit up with the surface. Now, this movement will cause extra loads on the bridge. So this is what the dynamic load allowance talks about. Basically, those uneven surface of the road will cause an additional load because when the car moves up, it will pressure the bridge more. This is not only because of uneven surfaces, also because sometimes your bridge itself is designed that way. It might be curved upwards. In this case, it's not a problem because curving upwards will relieve the force, but we still multiply by dynamic load allowance. Or sometimes it could be like curved like this for some reason. So there are a lot of reasons why you would be needing to multiply the live load by a factor to increase it. Anyway, now this happens because there is a relationship between the speed at which something is moving and the dynamic effects of the moving vehicle. This will not happen because unless you have Superman or Flash running here or even Goku, this will never happen at all. So you don't have dynamic load allowance. That's what I'm trying to say. So those things are really cool, and they are written here, and I will be talking about them in the draft here. I will be talking about the meanings of those things. But the first thing first, the code tells you to use 90 PSF, which means 90 pounds per square foot. Now this can be converted using all means of conversion. So a very quick online conversion, if you say 90 PSF to kilopascal, it gives you 4.3, which means that's not a lot to be honest. 4.31 kilonewtons per meter square. That's not a lot. Wait, I mean, when I designed my structures, I designed at 0.35 tons. So, I mean, when I designed my structure, I designed it to 3.5 kilonewton per meter square. This is my own live load. So, yeah, it's not really that much. I want to see something. So, 4.31 4.31 divided by 3.5. Is this 1.6? No, okay, never mind. The load suggested by the pedestrian design guide is 19 PSF, which is 4.31. And there is a really, really cool figure in the code that helps you understand live loads. I mean, take a look. This is really amazing. Like this just made values really, really good for me. It makes much sense. Let's take a look. Now, he shows you here live load 50 PSF, live load 100 PSF, live load or live load 150 PSF. So you can see that like this is possible. This is not really likely, and this is highly unlikely. But still, well, in the end, the word likely and unlikely is determined by the code, and the code determines 90 pounds per square foot. I want to talk about a little tangent here. It doesn't have anything to do with pedestrian bridges, but just occurred to me, and I want to talk about this. It's the concept of safety in codes. I don't know if I talked about this before in videos before on this channel, but I want to talk about this right now. So now, players, this has nothing to do with pedestrian bridges now. I want to just tell you the concept of code and safety inside codes. You see, the safety inside codes is basically a load factor, for example, 1.2 dead load plus 1.6 live load. This is called a factored load. This is ultimate load, they call. And you have a concept of safety, which means that if, for example, if a section carries 100 kilonewton per meter, you multiply it by a phi, which is a strength reduction factor, which is usually less than 1. What does this mean? Well, look, when you calculate this, when you calculate your dead load and you calculate your live load service, and you add them together, let's say you just add them together. If you have a kilonewton axis here and the probability axis here, this is a probability now. If you say dead load plus live load, let's say this is 120 kilonewtons. Let's just say that I have a column, for example, and dead plus live is 120 kilonewtons. Well, I go to my kilonewton scale, and this is 120 kilonewtons now. Of course, the probability of this happening is quite high because what you calculate here is actually the average of something called the natural distribution of loads. Because you are predicting, on average, for example, something dead load and something live load. Now, this is incorrect because, well, there is variation in dead load because you don't know exactly for sure what the thickness of a slab is. And there is a variation in live load because the only thing you can do is to predict the live load, although you don't know how the people will react. So the idea is that you have a distribution, a bell distribution like this, a normal distribution of your load curve. Now, what about your resistance curve? Your resistance curve, I need to video edit something very quickly here. Okay, so I quickly video edited this. With the power of video editing, I modified my drawing. So the resistance, let's say the same column in the nominal resistance or the resistance without factors of safety. Let's say the nominal resistance is, I don't know, like 300 kilonewtons. And of course, here once again, we have our 300 kilonewtons. And of course, the probability is high because what you calculate here is the average expected resistance. However, this is not necessarily the real resistance you will see in real life because your column might not be of the same dimensions that you assumed. Your material might be a bit weak. You might have problems in formwork. You might have all kinds of problems. You might not have perfect anchorage between steel and concrete, a plethora of possible reasons why this might not be the case. So you would have a distribution here, a Gauss distribution, like this. I'm going to be a little bit exaggerating here because I want to prove a point here. A Gauss distribution like this. So this is, let's say we have one column that is 300 kilonewtons. Now, is there a probability of failure? The answer is yes. The probability of failure is any position where the resistance is less than the applied load. So this region, if you take a look on this little region, you see that in this little region, it's characterized by the red curve being on the left side of the blue curve, meaning that the values of resistance are lower than the values of loads. Which means that even if you design your column to have 300 kilonewtons resistance, under a 120 kilonewton load, you would still have a very, very small probability, a very minute little probability, small, that there might be a failure. So what do codes do? Well, codes try to limit this probability of failure by introducing safety factors. Because when you design in reinforced concrete, you're not going to make a statistical analysis of all the stuff you're doing. In design, for a layman engineer, the only thing he wants to see is to see that phi Pn is more or equal to P ultimate. If the resistance is more or equal to the applied loads, then you say yes. And you don't care about all those nuances in the code. Why? Because the code takes this into account by applying factors of safety. It's more, there is more detail behind it. I want you to try think about it yourself. Okay, let me rephrase that. So this is what I see, and this is what the normal engineer sees. So how can I make this get a little bit closer to your opinion? You see, what the engineer sees is only a value. So let's say that we have this value. Let's say we calculate this value. And when we calculate this value, we think that maybe you get 180 or something. This is, of course, a increased value because 1.2 dead plus 1.6 live. Assume it's 180. So what you would see is, I don't know, maybe here, a value here, which is 180, for example. Or let's say, let's put it here, 180. And then you have a reduction factor. Of course, in columns not 0.9, in columns much less. So let's just say for a strange problem, I don't know, for some other problem, it's 200. So you have 180 here, you have 200 here. 200 is on the right side of 180, which means it's larger. So all is nice and dandy. And this is what codes do for you. They simplify this entire statistical mumbo jumbo into a very simple inequality that just gives you one little solution, one little problem. And in the end, when you design like this, you still run into a very small probability that your structure will fail. But of course, you cannot do more than this because there is no, in theory, theoretically speaking, there is no foolproof structure. So yeah, well, I just wanted to go on the tangent because we were talking about live loads and dead loads and or whatnot, all this kind of stuff. So I wanted to go into this tangent, talk about what it means to multiply by safety factors and load factors. And this is why I love teaching at universities. This is those things that it's kind of, I'm going to tell you a little insider information here. So when I teach at the university, sometimes I go on a tangent like this. And of course, the students, like 20% of them understand immediately what I'm saying, and the rest needs to revisit what I talked about later. So usually when I finish talking, I say, well, if you get this, good for you. If you didn't get this, you will still be able to get an A in my lecture, but if you get this, you will be a much better engineer in real life because you know the essence of what you're doing rather than just applying an inequality. Out of talk on the tangent, let's get back to our point here. The other thing that you need to take into account is something extra that we use for pedestrian bridges. It's called the collision protection for pedestrian bridges. You see, it's a little bit more dangerous for pedestrian bridges when compared to highway bridge. If this is a highway bridge, if there are cars here, then, well, you have your own clearances and your own max heights that you will impose on that thing. I mean, you see those things, those little signs where it says 5 meter maximum or something. Now, in pedestrian bridges, things get a little bit more spicy because there are people here. So any collision will harm people. But when you have a highway bridge, first of all, the car is not on the edge. And second of all, if a collision occurs, it's not the driver who will feel the collision, but the bridge, and the driver will not really get that injured because even if something flies into his face, there is a car that always will protect him. But when there is pedestrian standing here, then of course if anything flies his way, he will be the one who gets hurt. Now this is taken into account in the design, the draft of the code. There we go. It's in collision mitigation 1.3. It says that there is an increase in vertical clearance of 1 foot higher than highway bridges. So if you have here a clearance, if this is a highway bridge, and the code tells you need a clearance of, I don't know, like 5 meters, then for pedestrian bridges you need 5.3045 or something. You need to increase it by 1 foot because of all those things. Now, this is one thing that I wanted to talk about, the live load and the geometry here. The second thing I want to talk about is other types of live load. So there's something I started, like I was like really saying, really, that can happen? Well, yes, it can happen. There's something called equestrian load. I want to call it horse load, basically. So for me, I'm gonna ignore horse load. However, if for some reason you have, like, I don't know, either a royal bridge or a bridge in a rural area, maybe you want to account horse load into account. I'm not uh, I'm not gonna take this into account. I will not consider horses, to be honest. But well, you can see that there is some horse loads included. Now, with that being said, there is two things I want to talk about: a vehicular load and something called the wind load. Well, pedestrian bridges shall be designed for wind loads as specified in AASHTO, and it tells you the articles of that. And unless it's not defined by the owner, the importance factor is taken as 1.15. The load is applied over the exposed area in front of the elevation, including enclosures. So what is he trying to tell you? He's trying to tell you that there are wind loads applied on the bridge, and you need to take those into account. Why do you need to take those into account? Because when you take wind loads into account, first of all, your beam that is carrying this beam, this pre-stressed beam that is carrying the bridge, is going to be under biaxial bending, because there is one axis bending from the gravity loads and there's one axis bending from the horizontal loads. That's problem number one. Problem number two is those piers that carry the bridge are going to be like necessary to have also biaxial bending. One bending is due to the bridge, of course, if you assume a fixed connection. If you don't, then there is no bending. And the other thing is due to lateral bending. The third thing is due to stability, because you need to make sure that there is no sliding occurring here. It will not slide in the longitudinal area because there is ground on both sides. Like here, there is a ground, and there is a ground. But on the lateral side, it can slide and fall off. Of course, this is an exaggeration. You need to take this into account. You need to design your bearings here to be able to carry this horizontal load. So wind load is also partially required. What about fatigue loads? Well, you see, what is fatigue? I want to define it in a very simple way. Fatigue is the loss of strength under cyclic loading. The simplest thing is about talking about fatigue is talking about a paperclip like this. This is a very odd paperclip, the paperclip that everybody uses in his daily life. So how would I break this paperclip? If I want to break this paperclip, I will just take this edge, get it out, get it back in, and get it out, and keep repeating this cycle of tearing it out, tearing it in, back and forth, multiple times until it finally breaks here. So what did I do? Did I become Hercules? Was I able to apply forces more than 400 megapascals stress? No, I am not able to do that. The only thing that I was able to do is to reduce the yield strength from 400 to a much lower stress. Now, what are the things that affect how low my stress goes, or my strength goes? Well, the first thing is the amplitude of motion, because if you move it very far away back and forth, you will break it after, I don't know, 20 tries. But if you move it only slightly back and forth, you might need 100 tries to destroy it. That's the first thing. The second thing is the amount of force you apply. If, like, I try to break the paperclip, or Hulk Hogan, he's a legend in wrestling, very old, tries to break it, I think that Hulk Hogan will break it in 3 tries, whereas I need 20 or something. So there are two things. The first thing is called the amplitude of motion, and the second thing is, well, basically the force behind the motion. Of course, those two things plus a frequency of number of times will cause fatigue. That is what fatigue is. Of course, I am using a very simplified version of the definition. That is, of course, the amazing definition of scientists, but I am a scientist myself, I know. But I'm a guy who likes to simplify things as simple as possible. Because, I mean, look, I could sound smart and tell you the amazing definition with with perfect English articulation. I would sound smart, but then you would not understand. So I rather sound simple and make you become smart. All right. So what about fatigue load now? You see, fatigue load is extremely dangerous and needs to be taken into account, especially if you have an highway bridge that is continuous. Um, and we'll talk about this later, but if you have a highway bridge, oh, I messed up. If you have a highway bridge that is continuous, let's take a look between a highway bridge that is simply supported and a highway bridge that is continuous. Let's take a look on that. On the simply supported highway, let's say a truck is moving, and the truck is moving everywhere, okay? When the truck is moving, in every movement of the truck, there will be always a positive moment. Sometimes it looks like this, sometimes it looks like this, sometimes it looks like this, based on the position of the truck on the bridge. Of course, every position has its own moment diagram, and the combination of all possible moment diagrams is something what we call influence line. You can see that the influence line, or basically the moment diagrams, are on one side only, positive side. And by the way, I draw positive downwards, so like for some people like to draw positive upwards. I'm a downwards positive fan. Anyway, it's just a little thing I do. So you can see that the moment is always positive, so it's only a one-sided moment loading, which means this is your amplitude. This is your amplitude of loading. Let's take a look on the continuous. Let's take a look on the continuous bridge. When the truck is moving, well, sometimes let's take a look on this point, on this span now. Sometimes while the truck is moving, it is loading the. Of course, I'm drawing a moment diagram just very quickly. It doesn't look like that. It should be curved because it's an indeterminate structure. But nuances aside, what I'm trying to point here is that while the truck is moving, the moment diagram is shifting. And when the truck reaches this second, the second span, the moment diagram shifts and becomes negative, like this. Of course, not lines. It's different than lines. This is incorrect. I should curve it like this. But I told you before, I'm just doing it approximately here. So you can see that the moment diagram changes. That's what I'm trying to say. So when you have a continuous bridge, the amplitude of motion is much larger than a simply supported bridge. That's what I tried to say when I was talking about fatigue. Now, the amplitude check, we understood. What about the force? Now, luckily for you, and this is really luckily for us, to be honest, in pedestrian bridges, luckily for you, we don't use or we don't really care about fatigue too much in pedestrian bridges. Why? Because of the puny load that is moving. This is a joke in comparison to real structures. This is a joke in comparison to AASHTO highway bridges, where you have a lot of cars and trucks moving. So, because of the puny load, we don't take this into account in fatigue calculations. You might say, wait a minute, of course, you would think I might be joking here. No, I'm not joking, because this is what the code says. You can see that the fatigue loading used for the fatigue limit states shall be specified in section 11 of AASHTO, which is a load. And you can read here, neither the pedestrian live load or the maintenance vehicle load are used in the fatigue load. So we dodged the bullet here. Going on with this, and I wanted to read this document, it's really nice and important. It gives us so much insight here. I will be talking about the different things that are the AASHTO code here later in another video when we reach them. But for now, I need to give you an introduction video. So here is your introductory video. Before I finish here, you have a design truck. And the design truck here is different than the design truck of the AASHTO. The AASHTO has a much more powerful design truck. This is, or they call it design vehicle, to be honest. Sometimes they call it design tandem. This is a much smaller design tandem because it's a maintenance vehicle, and the maintenance vehicle is used for any bridge that is more than 7 foot and has the ability to allow maintenance trucks. For example, now this is a pedestrian bridge, and I think it's more than 7 feet wide. So I think this will allow for a maintenance vehicle to pass through. Are there bridges more than 7 feet with no maintenance vehicle? Yes, definitely. This, for example, this bridge, even if this bridge is more than 7 feet wide, it will not be designed for maintenance vehicles because there is no way for a maintenance vehicle to reach that position. The code actually says that. It says that where vehicular access is not prevented by physical methods, you should design if it's more than 7 feet, basically. What I'm trying to say is, if you have a 7 feet bridge and you do not restrict access to vehicles, then it needs to be designed for maintenance. Of course, you could, for example, have a ramp here, and it would allow for maintenance vehicles to enter the bridge. However, you can just put some posts here and prevent them from entering, which means then once again that you do not have maintenance vehicles to be passing through this. You see, it's the designer and owner's ability to limit or allow access of maintenance vehicles. Now, those maintenance vehicles, what are those? Well, they're called maintenance vehicles, but truth to be said, it's not always about repairing the bridge. I mean, the vehicles that are used to clean the bridge are also called maintenance vehicles. Of course, here you have your H1 and H5 and H10 vehicles. Those have the loads on each axis and the distance on each axis, and you will have to do an influence line. And we are going to do this in robots. We are going to try influence line in robot. Not only this, you see this live load? Well, it specifically tells you that you should move your live load to cause the maximum load effect. Pedestrian bridges shall be designed for uniform pedestrian loading of 19 psf 9T. This loading shall be patterned to produce the maximum load effects. We need to talk about this in robots. There is a lot of influence lining that is going to happen. I don't think I've talked in detail about influence lines before, so this is a good way of understanding it in robot. So, well, I think this is the most important things that are covered in this guide. I don't think I have anything else to add here. There is also the design and the resistance, and here every time it throws you back to the AASHTO LRFD. What it's basically telling you is, hey, here are your loads, and the rest just go to the AASHTO. We'll be talking about those values later when we do an Excel sheet to design those things. I will leave it for you to read, to take a look on it, and to check it out yourself in preparation for the next week. Now, I do apologize for having the video come out late for this Sunday. You see, the reason behind this is I was trying to find those specification or design guides. I was unable, and finally I found the draft. And it took me some time to verify that the draft is indeed as close as it gets to the real deal, because in the end I have a responsibility towards my viewers to give them the best possible material. That's everything I wanted to talk about. I hope that you enjoyed the video, and of course, if you have enjoyed the video and you found it beneficial for you, then please like, share, comment, and subscribe, especially subscribing because it helps increase the reach of my channel. This is the Civil Engineering Essentials channel, and we will catch you in the next video.